Vacuum mysteries, false vacuum, and metastability. There's one piece we've tiptoed around that could erase the whole board without fanfare: the vacuum itself. Not the absence of stuff, but the energy of empty space. The fields that still have values when everything else is gone. In our best tested physics, the Higgs field gives particles mass by settling to a non-zero value. It sits in a valley of potential energy. The question that keeps theorists cautious is whether we're in the deepest valley, the true vacuum, or just a local dip, a false vacuum that only looks stable because the walls are high and we haven't tunneled through. Standard model calculations, using measured Higgs and top quark masses, place us near a boundary. The numbers hint the electroweak vacuum might be metastable, long-lived but not guaranteed eternal. There are uncertainties, especially in the top mass and higher order effects, that blur the verdict. The safe bet is that if it's metastable, the lifetime is stupendously longer than any timescale we've named so far, far beyond black hole evaporation. But metastable doesn't mean forever. It means not yet. If a transition happens, it wouldn't start with a bang you could see coming. A quantum fluctuation at some point in space could nucleate a true vacuum bubble, a tiny region where the fields tip into a lower energy configuration. If that bubble beats surface tension, it becomes favorable to grow. Then it expands at a speed so close to light that warning is a meaningless word. The bubble wall sweeps forward, rewiring physics as it goes. The constants that set chemistry and particle masses could change. Electrons might be heavy or massless. Protons might be unstable or bound differently. Inside the bubble, familiar structures disintegrate into whatever the new rules allow. There's no pain, no time to react, and no privileged frame to spot the front arriving. One instant you exist, the next you're part of a different story. It sounds like a disaster movie. It's actually colder than that. There's no shockwave you can outrun, no shelter that helps. And crucially, the odds, given current estimates, are remote beyond comfort. If the vacuum is metastable, the decay rate per volume is so tiny that even integrated over an expanding universe and absurd spans, the expected waiting time is astronomical to the point of parity. We're not playing with a hair trigger. We're noting a theoretical possibility the equations allow. What nobody knew in the Bright Ages is how this risk threads the rest of the timeline. It doesn't depend on star formation, on black holes, or on the fate of protons. It rides on the shape of a potential we measure indirectly. The same framework that gave us the Higgs and predicted its interactions leaves a sliver of parameter space where a deeper valley exists. Small shifts in inputs move us between stable, metastable, and unstable. Our measurements put us in the middle category with a lot of caveats. That's why people talk about it with care. There's a common worry tied to human experiments. Could particle colliders trigger such a collapse? The short answer is no. High-energy cosmic rays crash into Earth's atmosphere and into other planets, stars, and interstellar gas, with energies far beyond anything human machines reach, and they've been doing it for billions of years across a vastly larger target. If such collisions could nucleate a bubble, the universe would have had ample chance to do it already. Safety studies addressed this specifically and concluded we're not uniquely dangerous. Nature has been running higher stakes tests at scale for eons. Meanwhile, the accelerated expansion plays a quiet role. If a bubble forms, it grows at near light speed relative to local space. Expansion stretches distances, but can't outrun a front moving through the fabric. In practical terms, if it starts anywhere in our future light cone, it arrives without forewarning. If it starts outside, we never know. There's no partial update, no horizon glow. Either we learn by being rewritten, or we never learn at all. So why include this chapter at all given the odds? Because it's honest about our ignorance, and because it frames heat death correctly. The slow fade we've been tracing assumes the vacuum holds. If it does, the universe drifts toward maximum entropy. Cold, thin, forgetful. If it doesn't, the end isn't heat death. It's replacement. Not fire, not noise, just a silent swap of rulebooks that annihilates the meaning of structure we've been using. Both outcomes are consistent with what we know. One is sedate, one is absolute. Here's the strange comfort. We don't need to pick the likely lifetime of metastability swamps every other clock. Black holes evaporate first. Proton debates resolve long before vacuum risk comes due. On human scales, even on planetary or galactic scales, the vacuum is steady enough to build civilizations, write histories, and argue about endings. We act inside a stability that's either true or long-lived enough to matter. If the vacuum holds, the dark era keeps thinning. If it flips, there's no epilogue, only new physics everywhere at once. Either way, our quiet ledger turns its next page. Big Rip, Heat Death, Big Crunch, framing the fates. We've sketched a universe that fades, not explodes. But before we let the clock run out, we have to ask what the expansion itself plans to do. The driver is dark energy, whatever's causing space to stretch faster over time. Its behavior is summarized by one number, W, the ratio of pressure to energy density. If W equals -1, dark energy acts like a cosmological constant, steady, unchanging, a uniform push. That's our best reading of the data today. If W drifts above or below, the N can look different. Start with the default W approximately -1. In this scenario, dark energy's density stays constant even as space grows. Matter thins, radiation redshifts, but the vacuum's push keeps the Hubble expansion from slowing much. Structures already bound, galaxies, clusters within their local wells, stay bound. Everything else recedes beyond communication. Temperature slides towards zero as free energy runs out. No catastrophe, just attrition. This is heat death. The name sounds dramatic, but it's really a description of maximum entropy, where gradients vanish and no engine finds a foothold. Meanwhile, there's a more reckless branch. W less than -1, sometimes called phantom energy. If the energy density increases with expansion, the push strengthens over time. Gravity doesn't just lose on large scales, it gets unbound locally. In the Big Rip picture, timing matters. Far in the future, clusters tear apart. Later, galaxies. Closer to the end, solar systems unglue. In the final moments, atoms themselves lose their grip, the space between particles dragged wider by a runaway expansion. Observations make this outcome unlikely. Constraints keep W very near -1, but they don't slam the door. It's a tail risk with a clear, brutal narrative. Then there's the nostalgic option, a big crunch. That would require the expansion to slow, stop, and reverse, bringing everything back together. In a universe dominated by matter, this was once plausible. With dark energy pushing outward, and with measurements showing flat or near-flat geometry and acceleration, a global recollapse looks ruled out for any constant W near -1. You'd need dark energy to switch off, or flip sign, or some new physics to emerge that turns the tide. It's not impossible in the space of all theories, it's just out of step with the data we've collected. What nobody knew in the Bright Ages is how precise these measurements could get. Supernovae as standard candles showed the acceleration first. The cosmic microwave background pinned geometry and matter content. Baryon acoustic oscillations traced expansion over time. Put together, they sketch a consistent picture. Cosmological constant fits. Drifts in W, if they exist, are small within current errors. That makes heat death the sober forecast, with quantified, shrinking uncertainties. If we keep it human, our branch of the story doesn't change much under any of these. Big Rip would truncate the long quiet with a dramatic finish. Yes, but on timescales that treat the age of galaxies like a footnote. Big Crunch requires a reversal we don't see signs of. Heat death keeps the timeline we've been following, a succession of dwindling engines until black holes evaporate and fields relax into cold. There's another subtlety. Even in heat death, maximum entropy isn't a single magic moment. It's an asymptote the universe approaches. As expansion continues, the maximum possible entropy grows because there's more space to fill with low-grade radiation, more horizon area for everything to smear across. The universe chases a moving target and never quite catches it, always sliding closer, never arriving. That's why the end feels like a limit, not a curtain. Dark energy's constancy also sets horizons that matter for observers. With W equals -1, each island universe is bounded by an event horizon, a limit to what can be seen or influenced. That horizon carries an entropy proportional to its area, a bookkeeping that echoes black hole thermodynamics. It's another way the cosmos enforces quiet. Even if you had perfect patience, there's a ceiling on the information you can gather from beyond your patch. The big shared conversation ends. Local talk remains. If, against current odds, W dipped below -1 and stayed there, the Big Rip would rewrite those horizons on a schedule. Bound systems would face deadlines. The math assigns dates. Clusters unbind millions of years before the end. Galaxies later. Planetary orbits closer still. Molecules in the final heartbeat. It's clinical and unnerving. But again, measurements push W close to -1, with no convincing evidence that it's crossing into phantom territory. Confidence matters here. Scientists don't just pick a favorite ending. They weigh models against data, then attach error bars. The consensus today, cosmological constant, heat death, comes with a known margin. Future surveys, better standard candles, gravitational lensing maps, and improved cosmic microwave background measurements will tighten the bounds on W and its possible evolution. Maybe the error bars shrink around -1. Maybe they drift slightly. Either way, the roadmap becomes clearer. So we file the fates properly labeled. Big Crunch, aesthetically tidy, observationally disfavored. Big Rip, cinematic, constrained but not eliminated. Heat death with a cosmological constant. Boring, relentless, and supported. That's the frame. No trumpets, no apocalypse, just physics, choosing the quiet path. Because the parameter happens to sit near -1. And with those candidates aired, the narrative returns to the long fade we've been tracing. It's not resignation, it's honesty about the slope we're on. The vacuum holds, the islands isolate, engines spend the last of their budgets, entropy writes its slow, legible script. We go back to the quiet timeline and let it run to the end. Timescales that break intuition, map of the far future. To feel what comes next, we need a ladder of time. Start at a heartbeat, 1 second. Stack them into minutes, hours, years. A human life, a few billion seconds. Civilization, 10,000 years, 300 billion seconds. Now we jump. The age of Earth, 4.5 billion years. The Milky Way's disk orbits in a couple 100 million. Already we're past experience. And yet, this is nothing. Climb again, 10 billion years. The cosmic noon we described, already in the rearview mirror. 100 billion. Most galaxies outside the local group slip beyond our reach. 1 trillion years. Red dwarfs rule the skies, patient and dim, with new star formation limping. 10 trillion. Many of those dwarfs still steady. The bright era is a rumor. 1 quadrillion, the first of the smallest red dwarfs start retiring into white dwarf embers. These numbers aren't decoration, they're the cadence of the remaining plot. Milestones anchor the map. The last truly new star, formed from cooling gas that somehow found a way to condense, flickers on somewhere between trillions and tens of trillions of years. The last supernova, likely from a delayed white dwarf detonation in a binary, fires much later, a final sharp spark in a dark field. White dwarfs keep cooling, their crystals growing, their light shifting past red into radio and beyond. Black dwarfs, the fully cooled corpses, won't exist until roughly 10 to the power of 15 years or later, depending on mass and composition. We've never seen one. The cosmos is too young. If proton decay is real, another clock ticks behind the scenery. Around 10 to the power of 34 to 10 to the power of 36 years, ordinary matter begins to thin from within. That process doesn't stop the gravitational rearrangements, but it edits the cast list, dissolving the solids that held long memories. If protons are stable, strange possibilities, like tunneling-driven fusions and dense remnants, stretch the activity, but only as a trickle. Either way, the big engines are quiet. The clean, universal clock belongs to black holes. The last stellar mass black holes evaporate somewhere near 10 to the power of 67 years. It's an absurd number that still counts as early compared with the giants. Supermassive black holes, the ones that anchor remnant galaxies, outlast everything. 100 quintillion years, a Googol, 10 to the power 100, and change, saw them radiate away their horizons in whispers, then brief shrieks. After that, the universe's inventory narrows to light, neutrinos, and any stubborn relics allowed by fundamental physics. This is where entropy's ledger matters. Complexity peaked early because free energy peaked early. The steepest gradients, the biggest drops from hot to cold, dense to sparse, existed when star formation was common and gas could cool fast. Structures, stars, planets, biospheres, cities, are machines that ride those gradients, turning them into local order. As the gradients flatten, the ability to build and maintain complexity fades. The universe doesn't forget how to make patterns. It runs out of what patterns feed on. Memory follows the same slope. Records are arrangements that resist noise. On short scales, we beat noise by active maintenance, recopying, shielding, error correcting. On cosmic scales, maintenance is a luxury that fails. Radiation flips bits, diffusion smooths edges, thermal noise jitters atomic positions, impacts and tides erase surfaces. Over millions of years, this is geology. Over trillions, it's a solvent. Push to 10 to the power of 30, 10 to the power of 40, and the question stops being what medium works and becomes what medium still exists. In a universe that's cooling and expanding, copies become ghosts, then statistics, then background. Here's the part that betrays intuition. Time dilates emotionally as it stretches physically. In a human story, a century carries weight. In a cosmic story, a century is the thickness of a line. Trillions of years will pass with fewer headline events than fit in a single astronomical catalog today. The important thing isn't the count, it's the scale. Once stars dim and black holes take over, waiting detaches from meaning. Engines that need differences go idle. Processes governed by tunneling and evaporation whisper across durations that bury language. So we draw a map in simple marks. Bright age, 0 to tens of billions of years. Galaxies, stars, chemistry, life possible in many pockets. Red dwarf age, trillions to quadrillions. Dim, stable, thrifty. Degenerate age up to 10 to the power of 15 and beyond. Embers cooling, collisions rare, archives failing. Black hole age, 10 to the power of 40 to 10 to 100 plus, gravity's vaults evaporating in the cold. Dark era, after fields, photons, neutrinos, and the last stubborn particles drifting in near equilibrium. Along the way, open questions attach dates, but don't change the contour. Proton decay shifts when solids dissolve. Vacuum metastability threatens a rewrite that ignores the schedule, but the best estimates put its odds so low and weights so high that the black hole calendar still runs. Big Rip needs a different value of W than we see. Big Crunch needs a reversal we don't measure. Confidence isn't arrogance, it's a claim to be updated by data. For now, the quiet path stands. We're left with a map that's honest about scale. You can climb it with exponents, but you can't feel it with memory. The future isn't a cliff, it's a desert. Wide and flat, where a few thin rivers run for unfathomable distances before soaking back into sand. The meaning, if we want any, isn't that nothing happens. It's that what matters happens early, when clocks still find purchase, and that the tail, long, cold, and patient, is the natural end of using differences well. The last flickers, quantum tails, and final decays. We're past engines, past horizons, past anything you could call weather. What's left are tails, the thin, stubborn probabilities that never quite hit zero. They don't build new stories. They tie off old ones with knots you almost can't see. This is where time turns from a road into a horizon, and where physics, still precise, speaks in the quietest register it has. If protons decay, that long verdict has basically cleared the stage by now. Any remaining baryonic matter has bled into leptons and radiation over spans that stretch to 10 to the power of 36 years and beyond, dissolving any last intricate arrangements into simpler pieces. If protons don't decay, the rubble persists, but only as cold, dense clumps with nothing left to do. Either way, the last power source with a schedule was Hawking radiation, and we watched it pay out. Now the universe is a ledger almost closed, with only quantum rounding errors left to sum. Those rounding errors still work. Quantum tunneling is the headline, an electron or nucleus facing a barrier it shouldn't cross, finding a path anyway because waves aren't edges. In dense, cold matter, tunneling fusion could trickle along at a rate that makes memory look instant. One reaction per chunk over times that make 10 to the power of 100 years feel like a weekend. If protons are stable, some models let iron-rich, ultra-dense clumps creep toward heavier nuclei via tunneling, slowing energy as neutrinos and faint photons. It doesn't reignite anything. It's erosion, not growth. Meanwhile, everything thermal is dragged thinner by expansion. Photons, already cold, keep redshifting. Neutrinos, barely social to begin with, drift as the baseline population. Gravitationally bound pockets, if any survived, are quiet to the point of parity. Sometimes, in absurdly rare coincidences, two relic particles scatter with a whisper of energy exchange. Sometimes, a metastable bound state rearranges, spitting out a low-energy quantum that adds almost nothing to the bath. These are events, not episodes. There is one piece of deep time that can sound like resurrection if you frame it wrong. Poincare recurrences. In a finite system with fixed energy, classical mechanics allows it to wander arbitrarily close to a previous microstate given enough time. Quantum mechanics has analogs, but the numbers are savage. Timescales double exponential in entropy. For any region with an event horizon, horizon entropy dominates, and the recurrence times are like 10 to the power of n, with n itself huge. They're not calendars. They're proofs that almost never can still be not never. They won't rebuild a city. They barely rebuild a fluctuation that looks like a puff of order before the bath dissolves it again. In de Sitter space, Such fluctuations are framed as Boltzmann fluctuations and are similarly inconsequential to sustained complexity. Micro-black holes might, in principle, flicker into existence as rare fluctuations in a de Sitter-like spacetime with a horizon temperature, then evaporate with quick flashes. They'd be the briefest candles in the deepest cave. Quantum borrowing paid back with interest in a tick. If the vacuum is exactly a cosmological constant, that horizon temperature stays, and such fluctuations are part of the long tail. If dark energy drifts off, even that stage whisper fades. Either way, no gradient lasts long enough to power anything complex.